JMB, how are you all? I hope you all are great. Welcome back to my YouTube channel. My name is Prince Ranpara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of the Technology, Ranpara. So in today's lecture, we are going to continue the solution of the industrial numerical example, right? So in today's lecture, we are going to mainly focus on the Packed Bed Reactor, right? So let's get started. In the previous lecture, lecture number 15, where we have calculated the weight of the catalyst required in order to achieve the desired conversion of 90% by using the Packed Bed Reactor, right? So in today's lecture, we are going to calculate and design the volume of the Packed Bed Reactor, right? So this lecture is in continuation with the previous lecture, lecture number 15, right? So let's get started. So in today's lecture, we are going to calculate and design the volume of the Packed Bed Reactor for the first order reaction kinetics for the given rate law minus Ra is equal to Kca, where the rate constant K is equivalent to 0.0002 cubic decimeter per hour kg catalyst, right? We are going to keep all the operating parameters to be constant, right? And we are solving it and we are designing, right? We are trying to analyze how large volume of the Packed Bed Reactor is required in order to achieve the desired conversion of 90% conversion, right? In the previous lecture, where we have calculated the weight of the catalyst by using the performance equation of the Packed Bed Reactor, right, which comes out to be weight of the catalyst, which comes out to be 1.727 into 10 raised to 5 kg catalyst, right, which is a very huge weight of catalyst is required in order to achieve the 90% conversion, right? If you want to recall, I request you to please watch the previous lecture, lecture number 15, okay? In this lecture, now, after knowing the how much weight of the catalyst we required in order to achieve the 90% conversion, we'll try to design the volume of the Packed Bed Reactor, right? For the same reaction where the reactance A is getting transformed into the new product B, right? Okay, where we are going to keep all the operating parameters to be constant. Okay, we are solving it for the first order reaction kinetics for the given rate law minus Ra is equal to Kca. Okay, now let's say we need to understand that how we will start, right, from where we need to beginning in order to design the volume of the Packed Bed Reactor. Okay, so we need to understand what is Packed Bed Reactor, right? So I request you to recall. See, the Packed Bed Reactor is the tubular reactor. Okay, so let's say the PFR is also tubular reactor, right? Then what is the principal difference between the plug flow reactor and the Packed Bed Reactor? The principal difference between the PFR and PBR is the Packed Bed Reactor, in which the hollow space of the tubular reactor is entirely filled by the solid packing, right? The solid packing can be a solid support, inert materials, or solid catalyst, right? Okay, so due to those reasons, the Packed Bed Reactor is differ. Due to those reasons, the Packed Bed Reactor differs from the plug flow reactor, right? Where in the case of plug flow reactor, where the entire hollow space of the tubular reactor is completely vacant, right? Is completely empty, right? From which the fluid will pass through the tube, okay, tubular space, and the reaction will take place, right? But in the case of Packed Bed Reactor, where the hollow space of the tubular reactor is completely filled with the packing materials, packing solid catalyst, right? Due to those reasons, the Packed Bed Reactor differs from the plug flow reactor. Okay, I hope up to here you have understood, right? Okay, but both the reactors are tubular reactors, right? Okay, now let's say, what if I tell you that, let's say, if we have the same dimension of the both reactors, right? If we have same dimension of the plug flow reactor and same dimension of Packed Bed Reactor, right? Same dimension, which means the length of the reactor, the width of the reactor, the breadth of the reactor, right? Breadth of the reactor. Okay, so by keeping constant, or by keeping the same dimension of both the reactors, PFR and Packed Bed Reactor, now how I will design my volume of the Packed Bed Reactor, right? So let's say the first approach is, let's say, if we are keeping the same dimension of both the reactors, PFR and Packed Bed Reactor, right? Both are the hollow tubular reactors, right? Yes. then both will have the same hollow space of the tubular reactor, right? Both will have same hollow space because both are the same tubular reactors, right? Okay, okay. The inner diameter and the outer diameter and the thickness is also kept constant of the reactors, right? Dimension of both the reactors are kept constant. Inner diameter, outer diameter, the thickness of the reactor is also kept constant. Okay, which means we can assume or we can think likewise that the volume of packed bed reactor is equivalent to the volume of plug flow reactor because both are tubular reactors, right? Right, because both are tubular reactors, both the reactors have the hollow space in, okay, in the tubular reactor. Then we can think in this approach that the volume of packed bed reactor is equivalent to the volume of plug flow reactor. Yes, if it is so, then let's understand how we will proceed further, right? So let's say in order to understand the in order to calculate and design the volume of the packed bed reactor, right, here we have understood that the volume of packed bed reactor is equal to the volume of plug flow reactor. Okay, now let's say, now recall what we have, how we have proceeded, right, in order to design the volume of the plug flow reactors, right? So we have utilized the performance equation of the plug flow reactor in order to design the volume of the plug flow reactor, right? The performance equation of the plug flow reactor is we have volume of plug flow reactor is equal to Fa naught integration of 0 to xa dxa upon minus Ra, right? So here we are considering that the volume of packed bed reactor is equivalent to the volume of plug flow reactor, right? Because both are tubular reactors, both have the same dimensions, both have the same inner diameter, outer diameter, both have the same thickness of the reactor. Due to those reasons, both are tubular reactors, both will have same hollow space, both will have same volume. Due to those reasons, let's say we are considering it that the volume of packed bed reactor will be equivalent to the volume of plug flow reactor, right? Will be equivalent to the right hand side, right? Which means we can write the volume of packed bed reactor equals to the right hand side, right? Which is Fa naught integration of 0 to xa dxa upon kc. Minus Ra is right here. Minus Ra is represent the rate law. So we are substituting minus Ra with its value, right? The rate constant and the concentration Ca. Okay, now we need to solve this integral form, right? So let's say the Fa naught represent the initial molar flow rate, right, which is constant, which is 6 moles per hour. Okay, the rate constant value is also constant, which is 0.3502 cubic decimeter per hour kg catalyst, right? Now here, which form of Ca we need to utilize, right? So recall, I have make you understand in the previous lecture, we have two forms of Ca, right? The first form of Ca is equal to 0.1 Ca naught, which is given in the question, right? The second form of Ca is equal to Ca naught into 1 minus Xa, right? So here we are going to use the second form of Ca which represent the fundamental relationship and also defines the conversion, right? So always remember, in order to design the volume of the packed bed reactors or plug flow reactors, in order to calculate, in order to solve the integral forms, in order to derive rate laws, we will always use the second form of Ca, right, which represent and define the conversion. Okay, so due to those reasons, we will use this second form of Ca, which is Ca is equal to Ca naught into 1 minus Xa. So in the place of Ca, we are substituting by its value, Ca naught into 1 minus Xa, right? So let's say we are now, which is equal to Fa naught divided by Kn Ca naught, right? So why Kn Ca naught came out of the integral? Because the rate constant value is constant, which is 0.3502 cubic decimeter per hour kg catalyst, and Ca naught is also constant, right, which is Ca naught is equal to 0.4 moles per cubic decimeter, right? So due to the constant value, right, we are taking K and Ca naught out of the integral, right? So finally we'll have integration of 0 to xa dxa upon 1 minus xa, right? Now we need to solve this integral form, right? So I have make you understand how we will solve this integral form in the previous lectures, right? So if you want to recall, I request you to please watch the previous lectures, right? So let's say the solution of this integral from 0 to xa dxa upon 1 minus xa comes out to be minus ln of 1 minus xa, right? Okay, now let's say we are substituting the integral form by its value, right? So finally we will get the volume of packed bed reactor is equal to fa naught divide fa naught into minus ln of 1 minus xa divided by k Cn naught, right? So finally here we have obtained the volume of the packed bed reactor is equal to fa naught into 1 minus 1 fa naught into minus of ln 1 minus xa divided by k Cn naught, right? I hope up to here you have understood, right? But wait, we need to think, right? Is this approach correct or not? We need to understand that, right? So let's say we need to understand, right? Because there is a principal difference between the packed bed reactor and the plug flow reactor, right? What is principal difference? The, let's say both are the tubular reactors, it is correct. Okay, both are of the same dimension, it is also correct. But the principal difference is the hollow space of the tubular reactor is completely filled by packing materials, right? So this is the principal difference in between the packed bed reactor and the plug flow reactor, right? In the case of plug flow reactor, where the hollow space of the tubular reactor is empty, right? So there are no packing materials in the plug flow reactor, right? Entire hollow space of the tubular reactor is empty. Okay, so this is the principal difference, right? So due to this principal difference, in order to design the volume of packed bed reactor, we need to consider lots of engineering aspects, right? Okay, so what are those? We need to understand that. Okay, so let's say the packed bed reactor, in which the packed bed reactor is tubular reactor, right? Okay, which have the hollow space. The hollow space of the tubular reactor is filled with the different packing materials. The packing materials can be a solid support, solid catalyst, inert material, or any support, right? So let's say, okay, which means if we are feeding the entire, if we are filling the entire hollow space of the tubular reactor by a solid catalyst, which means which consists of different shape and size of the solid catalyst, right? Let's say the packing materials will be of different shape and size, will have different particle size, right? Will have different bulk densities, will have different, okay, we'll have different bulk densities, right? If we are, what if we pack the packing materials very tightly? What if we peg the solid materials, solid catalyst very loosely, right? What will happen, right? We need to account all those things, and based on this we need to design the volume of the packed bed reactor, right? So due to those reasons, this approach of designing the volume of packed bed reactor is incorrect, right? The concept is correct, but partially it is incorrect, right? So we will never use this approach to calculate the volume of the packed bed reactor. Remember this, right? Okay, so this is where the most students will make, right? This is where the most students will get confused and will make mistake. Okay, so then what is the actual approach to design and calculate the volume of the packed bed reactor? We need to understand that. Okay, I hope up to here you have understood. Okay, so let's say in order to design and understand how we design, what are the important points we keep in mind to design the volume of the packed bed reactor, right? And what is the actual method to design the volume of the packed bed reactor? We'll understand that, right? So let's say this is the actual method to design the volume of the packed bed reactor, right? So let's say the volume of the packed bed reactor is the ratio of weight of the solid catalyst divided by its bulk density. Okay, so this is the actual method to design the volume of the packed bed reactor. Okay, so let's say here we'll understand all the terms individually. Okay, so PBR represent the volume of the packed bed reactor, W represent the weight of the catalyst, the rho B represent bulk density, right? Now here we will understand one more new term, which is bulk density. Okay. So let's say bulk density is the ratio of mass of the solid catalyst divided by total bed volume. Okay, so now we are going to understand one more important new concept, okay, fundamental concept in order to design the packed bed reactor, which is bulk density, right? So bulk density is the ratio of mass of the catalyst divided by the total bed volume. Okay, what does it mean? We'll understand in very simplified way. So let's say bulk density, which means the mass of the solid catalyst filled and divided by the total volume occupied by the solid catalyst, right? Okay, so let me make you understand in very simplified manner, right? So let's say in order to understand the bulk density, let's say here in this diagram I will make you understand what the term bulk density is, right? So let's say the diagram in the first case, right, the first here you can see both the diagrams, right? In this diagrammatic view where I have used measuring cylinder, right? So here we have first measuring cylinder in the first case, and in the second case I'm using same measuring cylinder, right? Which means I am keeping the volume of the measuring cylinder to be same, which means for the both the case I am using 100 ml of measuring cylinder, 100 ml volume of measuring cylinder, right, for the first case, and in the second case I am using again same 100 ml volume of measuring cylinder, right? Okay, up to here you have understood, right? Okay, now let's say in the first case, in order to understand bulk density, I will make you understand it very simplified. So for both the cases we are using same 100 ml volume of measuring cylinders, right? Okay, now remember this, we are using same spherical catalyst, right? The green spherical catalyst, right? The green circles represent the green spherical catalyst, right? With the same particle size, right? With the same shape and size. Oh, okay. And in the second case also we are using same spherical catalyst, right? With the same shape and size. Okay. So in both the case we are using same spherical catalyst. We are using same 100 ml volume of measuring cylinder for the both the case, right? Remember this. Okay. Okay, now let's say in the first case where we are feeding the spherical catalyst into the hollow space of the measuring cylinder, right? So let's say we have filled entire 100 ml volume of the measuring cylinder by 50 grams of solid catalyst, okay, which means we have loaded 50 grams of spherical solid catalyst, okay, and which occupies 100 ml volume of the measuring cylinder, right? So let's say come back to the definition of the bulk density, right? Bulk density is defined as the ratio of mass of the catalyst divided by total bed volume, or we can also say the bulk density is the ratio of mass of the solid catalyst divided by the total volume occupied by the solid catalyst, right? So let's say mass of the solid catalyst, which means for the first case the mass of the solid catalyst is 50 grams, okay. The total bed volume, which means the total volume occupied by solid catalyst, right? So here in the first case the total volume occupied by the solid catalyst is 100 ml volume is occupied by 50 grams solid spherical catalyst, right? Which means by using this formula will calculate the bulk density for the case 1. The row B1 defines the bulk density for the first case, which is mass of the solid catalyst, which is 50 grams, divided by the total bed volume, the volume occupied by solid catalyst, which is 100 ml volume, right? Entire 100 ml volume of measuring cylinder is occupied by 50 grams of solid spherical catalyst, right? So 50 grams divided by 100 ml, if we calculate, then the bulk density for the first case comes out to be 0.4, 0.5 gram per ml, right? The bulk density for the first case comes out to be 0.5 gram per ml, which means for 1 ml volume of the measuring cylinder we have 0.5 grams of solid spherical catalyst present, okay. I hope you have understood. Okay, so here now you can see visually, right? So visualize, you can see here the void space, right? The void space between the solid spherical catalyst is higher in the first case, right? Void fraction means the space between the solid catalyst, right? So see, these are the space between the solid catalyst, right? So in the first case we have higher void fraction. Okay, I hope up to here you have understood. Okay, now here we have completed the first understanding of the diagram 1. Now we'll understand the second diagram, right? So here again we are using the same volume of measuring cylinder, right? We are using 100 ml volume of measuring cylinder. Okay, and we are using same particle size of solid spherical catalyst. Okay, now let's see what will happen. So in the first case we have loosely pegged the solid catalyst to the measuring cylinder volume, right? Okay, so due to which we have very high void fraction. Okay, I hope you have understood. Okay, now let's say in the second case we are tightly packing solid catalyst into the given volume of measuring cylinder, right? Which means in the second case, now due to the tightly packing of the solid spherical catalyst, we were able to pack 65 grams weight of the solid catalyst into the same 100 ml volume of measuring cylinder, right? Okay, which means in the same 100 ml volume of measuring cylinder, we were able to fill 65 grams of solid catalyst, which means now we'll calculate the bulk density of the second case, right? So again, the bulk density is defined as the mass of catalyst divided by total volume occupied by solid catalyst, right? Okay, so in the second case, the rho b2 defines the bulk density of the second case, right? Which is the ratio of mass of the solid catalyst. The mass of the solid catalyst is 65 grams. 65 grams divided by the volume of the volume occupied by the solid catalyst, which is 100 ml, right? So 65 grams divided by 100 ml, right? So the bulk density for the second case comes out to be 0.65 gram per ml, which means for 1 ml volume of measuring cylinder, we have accommodate 0.65 grams of solid spherical catalyst, right? Okay, now I hope you have understood, right? Now let's say here visualize, you can see that, observe here, you can see what is the difference in the void fraction for the first case in comparison to the second case, right? So let's say you can observe here that in the first case we have higher void fraction, right? Void fraction, which means the space between the solid spherical catalyst, right? So in the first case we have very high void fraction, right? In comparison to the second case where we have tightly pegged the solid spherical catalyst into the given 100 ml measuring cylinder volume, right? So here, due to the tightly packing of the solid spherical catalyst, the void fraction decrease, right? So here you can see very lower void fraction between the solid spherical catalyst, right? Which means if the bulk density increases, the void fraction decreases, right? If the bulk density increases from 0.5 grams per ml to 0.65 gram per ml, right, the void fraction decreases. Okay, you can see that, right? I hope you have understood, right? Okay, so here we have understand what the term, how we define the bulk density in a very simplified manner, right? I hope you have understood that. Okay, so let's say now what will happen if the bulk density increases? What will happen? What if the bulk density decreases, right? Okay, so let's say we'll understand in a very broad perspective manner, right? So let's say if the bulk density is increased, which means the void fraction decrease, right? So due to the decrease in the void fraction, so why the void fraction decreases? Due to the tightly packing of the solid spherical catalyst, due to which the void fraction decrease, right? So due to a decrease in the void fraction, the pressure, there will be a very higher pressure drop, right? Pressure drop increases, right? Due to which the packing tightness, due to the reason of tightness in the packing, right? I hope you have understood. Okay, I hope up to here you have understood, right? So let's say in order to design the volume of the packed bed reactor, we required the weight of the catalyst and the bulk density of the solid catalyst, right? Okay. Now let's say for this case, we'll assume the bulk density to be 1000 kg per meter cube, which means 1 meter cube equals to 1000 liters, right? Which means 1000 kg of catalyst is loaded into the 1000 liter volume of the packed bed reactor, right? Okay, now see, we are assuming this. Okay, for in order to understand, in order to design the volume of the packed bed reactor, here we are assuming the bulk density to be 1000 kg per meter cube. Okay, the bulk density may vary, right? The bulk density may vary depending upon what type of packing materials we are using. Okay, I will make you understand in the further lecture, right? Now let's say up to here, I hope you have understood, right? Now there are two questions which will arise into your mind, which is, in order to calculate the bulk density, we required the total bed volume or the reactor volume. Okay, now but to calculate the reactor volume, right, to calculate the packed bed reactor volume, we need bulk density, right? So it looks circular, right? It looks circular, right? Isn't it? Okay, so let's say we'll understand that. I will make you understand in a very simplified way. Okay, so for that we need to understand the fundamentals concept of the bulk density, right? So let's say in this lecture I will make you understand in very brief. Okay, and in the upcoming lectures we will delve more deeper into the fundamental understanding of the designing aspect for the old reactors, right, where I will make you understand the fundamental detailed concepts of the bulk density and for the designing of the packed bed reactors, right? But in this lecture I will make you understand in very brief. Okay, so let's say, so on what all important points the bulk density depends upon. Okay, so bulk density depends upon what type of packing material which we are using, right? So let's say, right, so bulk density will depend upon the shape and size of the packing material. The bulk density will depend upon the void fractions, right? The bulk density will depend how we are packing it, right? If we are packing it very loosely or we are packing it very tightly, right? Okay, bulk density will also depend upon the pressure drop. Okay, so these are all the significant points on which the bulk density depends. Okay, but remember this, bulk density does not depend upon the reactor volume. Okay, bulk density does not depend on the reactor size. Okay, remember this. Okay, so how, I'll make you understand. Okay, so let's say in order to calculate the bulk density, we does not require the reactor size, right? We required the detailed specification of the packing materials, what type of packing materials which we are using, right? Okay, so we do not calculate bulk density from the reactor volume. Okay, remember this, we do not calculate bulk density from the reactor volume. Okay, we calculate bulk density primarily to make the use of bulk density in order to calculate the volume of the packed bed reactor, right? So first of all, we'll calculate bulk density, right, based on the packing material, right? Which type of packing materials we are going to load in the packed bed reactor, right? So based on the packing materials, based on the selection of the packing materials, we will firstly calculate the bulk density. Okay, and by calculating the bulk density, we'll use the bulk density value in order to design the volume of the packed bed reactor, right? Remember this. Okay, so this is the fundamental understanding of the bulk density. Okay, I hope you have understood. Okay, so after calculating the bulk density, we will finally calculate the reactor volume. Okay, I hope up to here you have understood, right? So let's say now we will solve the numerical example, right, for this question, right? Okay, so we are going to follow this actual approach to design the volume of the packed bed reactor, right? And here we are assuming the bulk density to be 1000 kg per meter cube. Okay, so let's say now we have weight of the catalyst, right? We have already calculated the weight of the catalyst by using the performance equation of the packed bed reactor, right? In the previous lecture, lecture number 15, and we have calculated the weight of the catalyst, right, which comes out to be 1.727 into 10 to 5 kg of catalyst, right? This huge weight of catalyst is required in order to achieve the 90% conversion, right? I hope you have understood. So from there we have the value of weight of the catalyst, right? Okay, now we have assumed the bulk density to be 1000 kg per meter cube. Okay, so we have both the values. We'll substitute both the values here and we'll calculate the volume of the packed bed reactor, right? So let's calculate. The volume of the packed bed reactor is equal to the weight of the solid catalyst divided by the bulk density, right? So the weight of the solid catalyst, which is 1.727 into 10 to 5 kg of catalyst, divided by the bulk density, which is 1000 kg per meter cube, right? 1000 kg per meter cube, right? So from numerator and denominator we can cancel off kg, right? Okay, and we'll remain with the cubic meter, right? So after calculating, we'll get the answer as volume of the packed bed reactor is equal to 172.7 meter cube, which means 1,72,700 cubic decimeter or liters, right? Which means a very huge volume of packed bed reactor is required in order to accommodate all this huge weight of catalyst, right? 1.727 into 10 raised to 5 kg weight of catalyst will be loaded into the 1,72,700 liters volume of the packed bed reactor, right? This is very huge volume and the huge weight of the catalyst, right? I hope you have understood. Okay, so here we have calculated the volume, we have calculated and designed the volume of the packed bed reactor, which comes out to be 1,72,700 cubic decimeter volume we will required, and weight of 1.727 into 10 to 5 kg catalyst is required in order to achieve the desired conversion of 90%, right? Right, where the reactants A are getting converted into the new product B, right, for the given first order reaction kinetics, where the rate law is minus RA is equal to KCA, right? I hope you have understood. So finally here we have completed the calculating and the designing of the volume of the packed bed reactor, right, for the first order reaction kinetics, right? I hope you have understood. So I request you to please make all the notes. Okay, now let's say now we will dwell more deeper into the fundamental understanding, right, in a very broad perspective manner, right? In a now we'll let's say now we'll do a very comparative real scenarios, right, in industries, how we design the packed bed reactor. Okay, so let's say okay so let's say we have calculated the weight of the catalyst by using the performance equation of the packed bed reactor, right, which comes out to be 1.727 into 10 to 5 kg catalyst, right? Okay, so for those reasons we will keep the weight of the catalyst to be constant, to be same, right? So we are keeping same weight of catalyst, which is 1.727 into 10 to 5 kg catalyst, right? Okay, now what if I change the bulk density? Okay, what so how the variation in the bulk density will affect my packed bed reactor volume, right? So what will happen if I change my bulk density? What if I increase my bulk density? What if I decrease my bulk density, right? So how does the changing in bulk density will affect the volume of the packed bed reactor, right? The packed bed reactor volume will increase or decrease in comparison to the in relation to the bulk density, right? Okay, now second is, what if I have increased my bulk density, or what if I decrease my bulk density? Then how does the bulk density relates to the pressure, right? If by increasing, if the pressure drop will increase or decrease. Okay, we'll understand that. Okay, so by increasing or decreasing the bulk density, what will change, right? Now how it relates to the void fraction by increasing or decreasing the bulk density, how it is going to affect the void fraction, right? The void fraction will increase or void fraction will decrease. We'll understand that. Okay, what will have effect of the bulk density on the packing tightness, right? So let's say we have here, we are going to compare 5 different things together, right? It will be very interesting. So remember this, we are going to compare bulk density, we are going to compare the pressure drop, the void fraction, okay, the packing tightness, okay, and the void fraction, right? So we are going to compare void fraction, reactor volume, pressure drop, bulk density, and packing tightness, right? So 5 different things we are going to do a comparative analysis, right? It is a real scenario in the industries, right? How we design the volume of the packed bed reactor, right? So it will be very interesting to understand. So understand, and okay, so understand carefully. Okay, so let's say for all these cases, we are keeping the same weight of catalyst which we have obtained by using the performance equation of the packed bed reactor, right? Which is 1.727, right? 1.727 into 10 raised to 5 kg catalyst, right? Okay, in the first case, where I have given the bulk density has equal to 1000, right? So this is the first case, right? By having the bulk density of 1000 kg per meter cube, we have obtained 1,72,700 cubic decimeter volume of packed bed reactor is required in order to achieve the 90% conversion. Okay, 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 okay. Now let's say, what if I increase my bulk density from 1000 to 2551, right? So what will have effect in the volume of the packed bed reactor? So by increasing the bulk density from 1000 to 2551, by using the same weight of catalyst, right, and by keeping both the values into the given equation of the volume of packed bed reactor, we calculated the volume of packed bed reactor, which comes out to be 67,699 cubic decimeter volume of packed bed reactor is required in order to achieve the same 90% conversion, right, for the first order reaction kinetics. Okay, which means by increasing the bulk density from 1000 to 2551, where you can see there is decrease in the volume of the packed bed reactor from 1,72,700 to 67,699 cubic decimeter, right? Which means by increasing the bulk density, the volume of the packed bed reactor decrease, right? Which means the void fraction decrease, right, due to the tightly packing of the solid catalyst, right? So by increasing the bulk density, the volume of the packed bed reactor decrease, the void fraction also decrease, due to which the packing tightness also increase, right? Due to which the pressure drop will increase. Okay, I hope you have understood. Okay, now let's say, now what if we furthermore increase my bulk density, right? So let's say, what if we furthermore increase the bulk density from 2551 to 4000 or 15,000, then what will happen? We'll understand that, right? So by increasing the bulk density from 2551 to 4000 or 15,000, where you can see for the same given weight, for the same calculated weight of the catalyst, you can see the volume of the packed bed reactor even decrease, right, from 67,699 cubic decimeter to 43,175 cubic decimeter to 11,513 cubic decimeter, which means by increasing the bulk density from 1000 to 2551 to 4000 and 50,000, which means by increasing the bulk density, the volume of the packed bed reactor decrease, right, and the void fraction also decrease, right? The void fraction, which means the space between the particles, right, decrease. Okay, solid catalyst particle decrease, right? So which means which will result in the tightness of the packing, right? Which means the packing tightness increase, right? Due to those reasons, which will result into a very huge pressure drop, right? Because there is very less void space available between the particles, due to which there will be an increase in the pressure drop, right? I hope you have understood. Okay, so I hope up to here you understood, right? So this is very way beyond expectation, right? Because 15,000 by density is too much, right? Which means we are, which means for this huge weight of catalyst, 1 lakh, which is 1.727 into 10 raised to 5 kg of catalyst, right? We are filling that huge amount of catalyst into a very small volume, right? 11,513 volume, cubic decimeter volume of the packed bed reactor, right? So we are trying to fill this huge volume of the huge weight of the catalyst into a very small volume of the packed bed reactor, right? Due to which the tightness of the packing will be too way beyond boundary point, right? Way beyond the expectation, right? Critical point, right? Which means we are tightly packing the solid catalyst, which means the bed density, the bed becomes more denser and denser, right? Due to which the void fraction will get decreased, due to which there will be increase in the pressure drop exponentially, right? There will be increase in the pressure drop exponentially, right? Okay, I hope you have understood, right? Okay, so let's say now in comparison to the increase in the bulk density, now what if I decrease the bulk density, then what will happen, right? So by decreasing the bulk density, how will it affect the volume of the packed bed reactor, the void fraction of the void fraction, right? The packing tightness, the pressure drop, how it will affect, we'll understand that. Okay, so let's say for as compared to the standard first case where we have kept the bulk density to 1000 kg per meter cube. Now let's say what if we decrease the bulk density from 1000 kg per meter cube to 500 kg per meter cube, then what will happen? We'll understand that, right? So let's say by decreasing the bulk density from 1000 kg per meter cube to 500 kg per meter cube, how will it affect in the volume of the packed bed reactor? But remember this, here we are keeping the same weight of the catalyst, which is 1.727 into 10 raised to 5 kg catalyst, right? So by decreasing the bulk density from 1000 to 500, after by keeping the same weight of the catalyst, by solving using the same equation, we can see there is an exponentially, there is a very drastically increase in the volume of the packed bed reactor, right? So see, from 1,72,700 to 3,45,400 cubic decimeter volume of the packed bed reactor is required, right? By decreasing the bulk density from 1000 to 500, we require 2 times the volume of the packed bed reactor as compared to the first case, right? Okay, so by the I hope you have understood, right? So by decreasing the bulk density, the void fraction increases, right? Which means the bed becomes loose, right? Due to which the void fraction increases, pressure drop decreases, the tightness of the packing decreases, right? I hope you have understood. Now what if we furthermore decrease the bulk density, then what will happen? We'll understand that. Let's say in comparison to the first case, if we furthermore decrease the bulk density from 1000 to 101 and 51, then what will happen? We'll understand that. Okay, so let's say by decreasing the bulk density from 1000 to 500, 101 and 51, where you can see there is a drastic exponential increase in the volume of the packed bed reactor for the same weight of the catalyst, right? Right, you can see the volume of the packed bed reactor increased from 3,45,400 cubic decimeter to 17,09,901 cubic decimeter to 33,86,275 cubic decimeter, right? Which is a drastic exponential increase in the volume of the packed bed reactor, right? Which is again way beyond expectation, right? Okay, you can see there is an exponential increase in the volume of the packed bed reactor, right? If we decrease the bulk density from 1000 to 500, 101 and 51, there is an exponential increase in the volume of the packed bed reactor, which comes out to be 33,86,275 cubic decimeter volume of the packed bed reactor is required in order to fill 1.727 into 10 raised to 5 kg of catalyst, right? And by using that system, we will achieve by carrying the reaction in the first order reaction kinetics, right? Where the reaction is carried in the first order reaction kinetics, where for the given rate law minus R is equal to KCA, will achieve 90% conversion, right, where the reactants A will get converted into the new product. Okay, we require a very huge volume of the packed bed reactor, which is 33,86,275 cubic decimeter, where we will have the bulk density to be 51 kg per meter cube, right? I hope you have understood, right? Which means by decreasing the bulk density, the void fraction increases, right? The pressure drop decreases, the tightness of the packing decreases, right? Okay, due to which the volume of the packed bed reactor increases, right? I hope you have understood, right? So, which means if we increase the bulk density, then the void fraction decreases, right? Bed becomes more tightly packed, right? If we increase the bulk density, which means the void fraction decreases, bed becomes more tightly packed, right? Bed will become more denser and denser, okay? Or which means less empty space between the particles, right? I hope you understood, right? So let's say we have the case one where we have loosely packing, right, where we have the higher void fraction, right, where in the case one where we have the higher void fractions, right, due to which we have very low bulk densities, right, and we require a very large reactor volumes, right. For the case two, right, where we are tightly packing the solid catalyst into the reactor volume, right, due to which we have very low void fractions, right, we have very low void fractions, right, and we have very high bulk density, right, we have very high bulk density, okay, and we require smaller reactor, we require smaller packed bed reactor. I hope you have understood, okay, which means the void fraction decreases, the pressure drop increases, void fraction increases, pressure drop decreases, right? I hope you have understood, right? So in order to summarize the entire today's lecture, right, so where we have understand, we have calculated and designed the volume of the packed bed reactor via new actual approach, right, which is correct, okay, and we have also understand one important concept, fundamental concept, right, in order to design the volume of the packed bed reactor, which is bulk density, right, bulk density, which is the ratio of mass of the solid catalyst to the total volume occupied by the solid catalyst, right, and we have understand what the bulk density means, how the bulk density, what are the factors on which the bulk density depends upon, right. Okay, finally we have calculated the volume of the packed bed reactor, right, and we have understood the real scenario of how we design the volume of the packed bed reactor, right. Okay, so in order to conclude this entire lecture, let's say I will try to make you understand in a very detailed broad perspective manner. We have understand in a very detailed broad perspective manner, right, where we have compared bulk density, right, how what are the effects of changing bulk density, right, what will happen. Okay, so if we increase the bulk density or if we decrease the bulk density, then how my void fraction will affected, right, how my pressure drop will get affected, how my volume of the packed bed reactor will affected, what will be the effect of the packing tightness, right. So let's say if the bulk density is increased, the void fraction decreases, right, due to the decrease in the void fraction, the reactor volume also decreases, right, which means the pressure drop will, as a result, the pressure drop will increase due to the tightly packing of solid materials into the reactor volume. Okay, I hope you have understood, right. So let's say in the second case, in comparison to the increase in the bulk density, now what if we decrease the bulk density, then how it will affect, right. So let's say if we decrease the bulk density, then the void fraction will increase, right, the reactor volume will also increase, right, and the pressure drop will decrease, the packing tightness will decrease, right, which means we'll have loosely packing of solid catalyst into the given reactor volume. Okay, I hope you have understood, right. So if you have any questions, then please comment below. I will try best to reply to all your comments, right, and I request you to please make all the notes. Okay, and I request you to please subscribe to my YouTube channel, please like the video, please share this video with your friends. Okay, and thank you for watching this video. Jai Ambe.